The concept of dimensions has evolved. We are moving beyond simple spatial directions into a framework of computational degrees of freedom. These 7 dimensions now serve as vital variables in high-dimensional data science, rather than just geometric axes. The first dimension is length. It is the most fundamental unit of spatial existence, representing a straight line that exists along a single axis. By adding another axis, we move beyond simple length into the second dimension. We move from 1 dimension to 2 by introducing the concept of width. Imagine a single line representing pure length. When we extend this line along a second perpendicular axis, we generate a plane. This is the foundation of 2-dimensional geometry. In 2 dimensions, every point is defined by 2 coordinates, an x and a y value, defining both length and width. This plane is where all flat shapes exist. Without width, we are restricted to a single direction. With it, we gain an entire surface. The third dimension is defined by depth. While length and width establish a 2-dimensional plane, the addition of the z-axis gives us our observable 3-dimensional reality. By introducing the z-axis, we gain the capacity to measure volume and spatial presence. This transition transforms a flat surface into a tangible object. This depth is what allows us to navigate our physical world, turning simple coordinates into a universe of volume. We live in a world defined by length, width, and depth. These 3 spatial dimensions tell us exactly where an object is located in our environment, but these coordinates are incomplete. To truly track an object, we need a 4th coordinate, time. This is the relativistic fold that integrates duration into our 3-dimensional reality. Think of time-lapse cinematography. By capturing moments over a duration, we see light trails, the path of existence through the 4th dimension. In this space-time manifold, every event is a point in a 4-dimensional grid, combining where and when into a unified structure. We move beyond our observable reality into the quantum manifold. These are dimensions 5 through 7. Unlike our spatial dimensions, these are compressed, hidden layers within the fabric of space-time. In this manifold, fundamental forces like gravity and electromagnetism converge into a single, unified framework. These higher dimensions are the key to understanding the quantum architecture of our universe. The 5th dimension introduces the concept of potentiality. Unlike the fixed path of the 4th dimension, the 5th dimension allows space-time to branch into multiple possible realities. In quantum computing, we represent these as variable states. By navigating these branches, we can process data far beyond the limits of linear 3-dimensional logic. This dimensional framework is currently being harnessed to stabilize data packets, moving us closer to a truly quantum future. The 6th dimension introduces probability bridges. These are geometric connections within the quantum manifold that link disparate states. By navigating these bridges, quantum particles can bypass spatial distance entirely, manifesting entanglement across the universe. What appears as a vast separation in our 3-dimensional world is revealed to be a simple, singular connection in the 6th dimension. The 7th dimension represents the unified manifold. Here, all fundamental forces are unified within the intricate geometry of the Calabi-Yau space. This space describes the totality of all possible quantum physical states, weaving together the fabric of our universe into a single, cohesive framework. In this 7th dimension, the separation between forces disappears, leaving only the pure, abstract geometry of existence itself. The Dimensional Mapping Project, initiated in 2026, marks a pivotal shift in quantum physics. Researchers at CERN have successfully isolated and unfolded a variable within the 5th dimension. By manipulating vacuum states, the team created a bridge that allows for data transmission across quantum states, bypassing traditional spatial latency. This breakthrough effectively maps high-dimensional variables into manageable computational units, opening the door for instant information flow. We are witnessing a paradigm shift. Researchers are moving from theorizing about higher dimensions to physically observing them in controlled vacuum states. By unfolding a 5th-dimensional variable within a quantum system, we can observe information packets without traditional spatial latency. This breakthrough marks the transition from abstract math to a new foundation for high-speed data architecture. In modern science, we move beyond three-dimensional space to process complex data. This is high-dimensional data science. Data sets today exist in many dimensions. We process these not as static shapes, but as variables in a multidimensional field. By mapping these into a high-dimensional space, our neural architectures identify patterns that are impossible to perceive in three dimensions. This allows us to handle variables that previously were considered noise, essentially folding dimensions to extract hidden intelligence. In 2026, researchers in Singapore introduced the Labyrinth Neural Network. This architecture represents a major shift in how AI handles complex data. Unlike standard models that process information in limited spatial dimensions, the Labyrinth network maps data across 7 distinct latent dimensions simultaneously. By navigating these 7 layers, the Labyrinth captures deep, nonlinear relationships, allowing for faster and more accurate pattern recognition than ever before. This evolution in neural architecture is redefining the boundaries of machine learning intelligence. In the high-altitude labs of the Swiss Alps, researchers are pushing the boundaries of physics. They are observing particles that act as if they are linked through a 6-dimensional bridge. These quantum entanglement ports effectively bypass spatial distance, suggesting a fundamental architecture beyond our 3-dimensional reality. In our standard 3-dimensional space, data transmission is limited by the speed of light, creating unavoidable latency over long distances. By leveraging higher dimensional manifolds, we can create a shortcut, a fold in the fabric of space that connects 2 points instantly, bypassing spatial distance entirely. This effectively eliminates latency, enabling real-time synchronization of data, regardless of physical separation, a cornerstone of hyperdimensional computing. We are currently witnessing a shift toward dimensional compression. This process translates complex data structures from 7-dimensional AI models into formats we can actually perceive. By distilling these high-dimensional variables, we create a bridge. This allows architects and engineers to interact with deep insights as if they were simple 3D models. This holographic workspace acts as a translator, turning the hidden logic of 7-dimensional neural architectures into actionable spatial intelligence. By the year 2030, our workspaces will transcend the limitations of 2-dimensional screens. Traditional desk-based computing will evolve into immersive, holographic environments. These workspaces utilize 7 dimensions of data, mapping not just spatial location, but also temporal intent. By anticipating user needs through high-dimensional data, the system prepares information before a task is even initiated. This is the integration of temporal intent into the user experience. We are entering an era where depth, intent, and reality converge, transforming how we interact with the digital universe. Leading physicist Dr. Elena Vance highlights the shift in our scientific approach to high-dimensional architecture. She notes, we no longer ask if these exist, we ask how much bandwidth we can extract. A massive economic shift is underway. As of 2026, the global tech sector has redirected capital, resulting in a 42% surge in research and development funding dedicated specifically to hyperdimensional computing. This pivot reflects a major transition as firms shift from traditional spatial architecture toward leveraging the massive computational bandwidth found in higher dimensions. By moving beyond 3D constraints, industries aim to solve problems previously thought to be impossible, effectively capturing the value of hidden degrees of freedom in data. This is more than just a trend. It is a strategic pivot that is redefining the future of global technology, trading physical limitations for infinite computational potential. We perceive the universe through 3 spatial dimensions. This is the bedrock of our human experience. To visualize the invisible, we must expand our perspective beyond spatial boundaries. By mapping variables across 7 dimensions, we bridge the gap between simple perception and the complex, hidden architecture of the universe. Lighting and color serve as our guides, translating these high-dimensional shifts into meaningful data. We are entering a pivotal era in human science. The goal has shifted from mere theoretical observation of higher dimensions to harnessing them for functional utility. By viewing these dimensions as degrees of freedom, researchers are now designing protocols to utilize them, turning abstract mathematics into the next frontier of computing and energy. This transition marks our evolution into a species that shapes its reality using the architecture of the universe itself.